There are still lots of things about space that we may never be able to answer, like, is time travel possible? Or are aliens living somewhere else in the Milky Way? But there is one thing I believe about space. Space is trying to kill me. Space isn't out to get me personally. It's also trying to kill you and everybody else. Think about it. Space doesn't naturally have what we need to survive when we travel there. No air, it's too hot or too cold. No ozone to protect us from those nasty UV rays either. This all sounds bad, but what can space really do to me if I stay on Earth? What we need to understand is that objects in space can cause people to think their days are numbered, even when there are events on Earth that can hurt or kill us before something from space does. So what are the odds that one of these objects will really affect Earth and you and me in our lifetime? Well, we can take what we know about the universe to try and figure that out. You might have heard stories about asteroids hitting the Earth. That would be pretty bad. Scientists think asteroids might have killed off most of the dinosaurs. Sounds like something we should worry about, right? Well, astronomers can now watch asteroids in space and see them coming using complex computer models to predict the deadly rock's path. For a while, the reported odds that asteroid Apophis would strike Earth in 2036 were once 1 in 625. But after updating their data, astronomers now say the chances are extremely low. Okay, what about the sun? Hollywood movies like to pick on our sun by showing Earth destroyed by solar flares or the sun dying out, which would cause Earth to freeze. Astronomers predict our sun contains enough gas to make energy for another 3 to 5 billion years. So, in 3 to 5 billion years, if people still exist on Earth, they'll have to deal with that. But today, well, we're safe. Sometimes the sun does shoot flares at Earth, but the magnetic field surrounding our planet blocks most of that radiation. The radiation that does get through creates things like the aurora borealis. Gigantic solar flares can mess with our satellites and electrical equipment, but the chances of it killing you are pretty slim. Okay, what about that supermassive black hole in the middle of our galaxy? What happens to Earth and us when it pulls us in? After all, it is supermassive. Nope, not going to happen. That's one big object that can't bother us. How can we be so sure? Our solar system is on the edge of the Milky Way, while the nearest supermassive black hole is about 26,000 light years from Earth. That means we aren't on that black hole's menu. So you still think space objects are trying to kill you even after what I've told you so far? I think I've even convinced myself that odds are really good that space and the objects up there won't kill me after all. But I'll probably keep looking up just to make sure nothing is headed my way.
Cloudy climate change. How clouds affect Earth's temperature. Earth's average surface temperature has warmed by 0.8 Celsius since 1750. When carbon dioxide concentrations in the atmosphere have doubled, which is expected before the end of the 21st century, researchers project global temperatures will have risen by 1.5 to 4.5 degrees Celsius. If the increase is near the low end, 1.5 Celsius, then we're already halfway there, and we should be more able to adapt, with some regions becoming drier and less productive, but others becoming warmer, wetter and more productive. On the other hand, a rise of 4.5 degrees Celsius would be similar in magnitude to the warming that's occurred since the last glacial maximum 22,000 years ago, when most of North America was under an ice sheet 2 kilometers thick. So that would represent a dramatic change of climate. So it's vitally important for scientists to predict the change in temperature with as much precision as possible so that society can plan for the future. The present range of uncertainty is simply too large to be confident of how best to respond to climate change. But this estimate of 1.5 to 4.5 Celsius for a doubling of carbon dioxide hasn't changed in 35 years. Why haven't we been able to narrow it down? The answer is that we don't yet understand aerosols and clouds well enough. But a new experiment at CERN is tackling the problem. In order to predict how the temperature will change, scientists need to know something called Earth's climate sensitivity, the temperature change in response to a radiative forcing. A radiative forcing is a temporary imbalance between the energy received from the sun and the energy radiated back out to space, like the imbalance caused by an increase of greenhouse gases. To correct the imbalance, Earth warms up or cools down. We can determine Earth climate sensitivity from the experiment that we've already performed in the industrial age since 1750, and then use this number to determine how much more it will warm for various projected radiative forcings in the 21st century. To do this, we need to know two things. First, the global temperature rise since 1750, and second, the radiative forcing of the present-day climate relative to the pre-industrial climate. For the radiative forcings, we know that human activities have increased greenhouse gases in the atmosphere, which have warmed the planet. But our activities have at the same time increased the amount of aerosol particles and clouds, which have cooled the planet. Pre-industrial greenhouse gas concentrations are well measured from bubbles trapped in ice cores obtained in Greenland and Antarctica, so the greenhouse gas forcings are precisely known. But we have no way of directly measuring how cloudy it was in 1750, and that's the main source of uncertainty in Earth's climate sensitivity. To understand pre-industrial cloudiness, we must use computer models that reliably simulate the processes responsible for forming aerosols and clouds. Now, to most people, aerosols are the thing that make your hair stick, but that's only one type of aerosol. Atmospheric aerosols are tiny liquid or solid particles suspended in the air. They are either primary, from dust, sea spray salt, or burning biomass, or secondary, formed by gas-to-particle conversion in the atmosphere, also known as particle nucleation. Aerosols are everywhere in the atmosphere, and they can block out the sun in polluted urban environments or bathe distant mountains in a blue haze. More importantly, a cloud droplet cannot form without an aerosol particle seed. So without aerosol particles, there'd be no clouds. And without clouds, there'd be no fresh water. The climate would be much hotter, and there would be no life. So we owe our existence to aerosol particles. However, despite their importance, how aerosol particles form in the atmosphere and their effect on clouds are poorly understood. Even the vapors responsible for aerosol particle formation are not well established, because they're present in only minute amounts, near 1 molecule per million molecules of air. This lack of understanding is the main reason for the large uncertainty in climate sensitivity and the corresponding wide range of future climate projections. However, an experiment underway at CERN, named, perhaps unsurprisingly, CLOUD, has managed to build a steel vessel that's large enough and has low enough contamination that aerosol formation can, for the first time, be measured under tightly controlled atmospheric conditions in the laboratory. In its first 5 years of operation, CLOUD has identified the vapors responsible for aerosol particle formation in the atmosphere, which include sulfuric acid, ammonia, amines, and biogenic vapors from trees. Using an ionizing particle beam from the CERN proton synchrotron, CLOUD is also investigating if galactic cosmic rays enhance the formation of aerosols and clouds. This has been suggested as a possible unaccounted natural climate forcing agent, since the flux of cosmic rays raining down on the atmosphere varies with solar activity. So CLOUD is addressing two big questions. Firstly, how cloudy was the pre-industrial climate, and hence, how much have clouds changed due to human activities? That knowledge will help sharpen climate projections in the 21st century. And secondly, could the puzzling observations of solar climate variability in the pre-industrial climate be explained by an influence of galactic cosmic rays on clouds? Ambitious but realistic goals when your head's in the clouds.
Watch the center of this disc. You are getting sleepy. No, just kidding. I'm not going to hypnotize you. But are you starting to see colors in the rings? If so, your eyes are playing tricks on you. The disc was only ever black and white. You see, your eyes don't always capture the world as a video camera would. In fact, there are quite a few differences, owing to the anatomy of your eye and the processing that takes place in your brain and its outgrowth, the retina. Let's start with some similarities. Both have lenses to focus light and sensors to capture it. But even those things behave differently. The lens in a camera moves to stay focused on an object hurtling towards it, while the one in your eye responds by changing shape. Most camera lenses are also achromatic, meaning they focus both red and blue light to the same point. Your eye is different. When red light from an object is in focus, the blue light is out of focus. So why don't things look partially out of focus all the time? To answer that question, we first need to look at how your eye and the camera capture light: photoreceptors. The light-sensitive surface in a camera only has one kind of photoreceptor that is evenly distributed throughout the focusing surface. An array of red, green, and blue filters on top of these photoreceptors causes them to respond selectively to long, medium, and short wavelength light. Your eye's retinas, on the other hand, have several types of photoreceptors, usually 3 for normal light conditions, and only 1 type for low light, which is why we're colorblind in the dark. In normal light, unlike the camera, we have no need for a color filter because our photoreceptors already respond selectively to different wavelengths of light. Also, in contrast to a camera, your photoreceptors are unevenly distributed, with no receptors for dim light in the very center. This is why faint stars seem to disappear when you look directly at them. The center also has very few receptors that can detect blue light, which is why you don't notice the blurred blue image from earlier. However, you still perceive blue there because your brain fills it in from context. Also, the edges of our retinas have relatively few receptors for any wavelength light, so our visual acuity and ability to see color falls off rapidly from the center of our vision. There is also an area in our eyes called the blind spot, where there are no photoreceptors of any kind. We don't notice a lack of vision there because, once again, our brain fills in the gaps. In a very real sense, we see with our brains, not our eyes. And because our brains, including the retinas, are so involved in the process, we are susceptible to visual illusions. Here's another illusion caused by the eye itself. Does the center of this image look like it's jittering around? That's because your eye actually jiggles most of the time. If it didn't, your vision would eventually shut down because the nerves on the retina stop responding to a stationary image of constant intensity. And unlike a camera, you briefly stop seeing whenever you make a larger movement with your eyes. That's why you can't see your own eyes shift as you look from one to the other in a mirror. Video cameras can capture details our eyes miss, magnify distant objects, and accurately record what they see. But our eyes are remarkably efficient adaptations, the result of hundreds of millions of years of co-evolution with our brains. And so what if we don't always see the world exactly as it is? There's a certain joy to be found watching stationary leaves waving on an elusive breeze, and maybe even an evolutionary advantage. But that's a lesson for another day.
It's midnight, and all is still, except for the soft skittering of a gecko hunting a spider. Geckos seem to defy gravity, scaling vertical surfaces and walking upside down without claws, adhesive goos, or superpowered spiderwebs. Instead, they take advantage of a simple principle, that positive and negative charges attract. That attraction binds together compounds like table salt, which is made of positively charged sodium ions stuck to negatively charged chloride ions. But a gecko's feet aren't charged, and neither are the surfaces they're walking on. So, what makes them stick? The answer lies in a clever combination of intermolecular forces and structural engineering. All the elements in the periodic table have a different affinity for electrons. Elements like oxygen and fluorine really want electrons, while elements like hydrogen and lithium don't attract them as strongly. In atom's relative greed for electrons, it's called its electronegativity. Electrons are moving around all the time and can easily relocate to wherever they're wanted most. So when there are atoms with different electronegativities in the same molecule, the molecule's cloud of electrons gets pulled towards the more electronegative atom. That creates a thin spot in the electron cloud where positive charge from the atomic nuclei shines through, as well as a negatively charged lump of electrons somewhere else. So the molecule itself isn't charged, but it does have positively and negatively charged patches. These patchy charges can attract neighboring molecules to each other. They'll line up so that the positive spots on one are next to the negative spots on the other. There doesn't even have to be a strongly electronegative atom to create these attractive forces. Electrons are always on the move, and sometimes they pile up temporarily in one spot. That flicker of charge is enough to attract molecules to each other. Such interactions between uncharged molecules are called van der Waals forces. They're not as strong as the interactions between charged particles, but if you have enough of them, they can really add up. That's the gecko's secret. Gecko toes are padded with flexible ridges. Those ridges are covered in tiny hair-like structures, much thinner than human hair, called setae. And each of the setae is covered in even tinier bristles called spatulae. Their tiny spatula-like shape is perfect for what the gecko needs them to do, stick and release on command. When the gecko unfurls its flexible toes onto the ceiling, the spatulae hit at the perfect angle for the van der Waals force to engage. The spatulae flatten, creating lots of surface area for their positively and negatively charged patches to find complementary patches on the ceiling. Each spatula only contributes a minuscule amount of that van der Waals stickiness. But a gecko has about 2 billion of them, creating enough combined force to support its weight. In fact, the whole gecko could dangle from a single one of its toes. That super stickiness can be broken, though, by changing the angle just a little bit. So, the gecko can peel its foot back off, scurrying towards a meal or away from a predator. This strategy, using a forest of specially shaped bristles to maximize the van der Waals forces between ordinary molecules, has inspired man-made materials designed to imitate the gecko's amazing adhesive ability. Artificial versions aren't as strong as gecko toes quite yet, but they're good enough to allow a full-grown man to climb 25 feet up a glass wall. In fact, our gecko's prey is also using van der Waals forces to stick to the ceiling. So the gecko peels up its toes and the chase is back on. Sometimes, when a fish is reeled up to the surface, it will appear inflated, with its eyes bulging out of their sockets and its stomach projecting out of its mouth, as if it's been blown up like a balloon. This type of bodily damage, caused by rapid changes in pressure, is called barotrauma. Under the sea, pressure increases by 14.7 pounds per square inch for every 33-foot increase in depth. So take the yellow-eye rockfish, which can live as deep as 1,800 feet, where there's over 800 pounds of pressure on every square inch. That's equivalent to the weight of a polar bear balancing on a quarter. Now, Boyle's gas law states that the volume of a gas is inversely related to pressure. So, any air-filled spaces like a rockfish's swim bladder or human lungs will compress as they descend deeper and expand as they ascend. After a fish bites a fisherman's hook and is quickly reeled up to the surface, the air in its swim bladder begins to expand. Its rapid expansion actually forces the fish's stomach out of its mouth, while the increased internal pressure pushes its eyes out of their sockets, a condition called exophthalmia. Sometimes rockfish eyes will even have a crystallized appearance from corneal emphysemas, little gas bubbles that build up inside the cornea. Thankfully, a scuba diver doesn't have a closed swim bladder to worry about. A diver can regulate pressure in her lungs by breathing out as she ascends, but must be wary of other laws of physics that are at play under the sea. Henry's law states that the amount of a gas that dissolves in a liquid is proportional to its partial pressure. The air a diver breathes is 78% nitrogen. At a higher pressure under the sea, the nitrogen from the air in a scuba tank diffuses into a diver's tissues in greater concentrations than it would on land. If the diver ascends too quickly, this built-up nitrogen can come out of solution and form microbubbles in her tissues, blood, and joints, causing decompression sickness, aka the bends. This is similar to the fizz of carbon dioxide coming out of your soda. Gas comes out of solution when the pressure is released, but for a diver, the bubbles cause severe pain and sometimes even death. Divers avoid falling victim to the bends by rising slowly and taking breaks along the way, called decompression stops, so the gas has time to diffuse back out of their tissues and to be released through their breath. Just as a diver needs decompression, for a fish to recover it needs recompression, which can be accomplished by putting it back in the sea. But that doesn't mean fish should just be tossed overboard. An inflated body will float and get scooped up by a hungry sea lion or pecked at by seagulls. There's a common myth that piercing its stomach with a needle will let air escape, allowing the fish to swim back down on its own. But that is one balloon that shouldn't be popped. To return a fish properly to its habitat, fishermen can use a descending device instead, to lower it on a fishing line and release it at the right depth. As it heads home and recompression reduces gas volume, its eyes can return to their sockets and heal, and its stomach can move back into place. This fish will live to see another day, once more free to swim, eat, reproduce, and replenish the population.
There is a curse that has plagued humanity since ancient times. The Greeks fought it by chewing aromatic resins, while the Chinese resorted to eggshells. In the ancient Jewish Talmud, it's even considered legal grounds for divorce. This horrible scourge is halitosis, otherwise known as bad breath. But what causes it, and why is it so universally terrifying? Well, think of some of the worst odors you can imagine, like garbage, feces, or rotting meat. All of these smells come from the activity of microorganisms, particularly bacteria. And as disgusting as it may sound, similar bacteria live in the moisture-rich environment of your mouth. Don't panic. The presence of bacteria in your body is not only normal, it's actually vital for all sorts of things like digestion and disease prevention. But like all living things, bacteria need to eat. The bacteria in your mouth feed off of mucus, food remnants, and dead tissue cells. In order to absorb nutrients through their cell membranes, they must break down the organic matter into much smaller molecules. For example, they'll break proteins into their component amino acids, and then break those down even further into various compounds. Some of the foul-smelling byproducts of these reactions, such as hydrogen sulfide and cadaverine, escape into the air and waft their way towards unsuspecting noses. Our sensitivity to these odors and interpretation of them as bad smells may be an evolutionary mechanism warning us of rotten food and the presence of disease. Smell is one of our most intimate and primal senses, playing a huge role in our attraction to potential mates. In one poll, 59% of men and 70% of women said they wouldn't go on a date with someone who has bad breath, which may be why Americans alone spend $1 billion a year on various breath products. Fortunately, most bad breath is easily treated. The worst-smelling byproducts come from gram-negative bacteria that live in the spaces between gums and teeth, and on the back of the tongue. By brushing and flossing our teeth, using antibacterial mouthwash at bedtime, gently cleaning the back of the tongue with a plastic scraper, and even just eating a healthy breakfast, we can remove many of these bacteria and their food sources. In some cases, these measures may not be enough due to dental problems, nasal conditions, or rarer ailments such as liver disease and uncontrolled diabetes. Behaviors like smoking and excessive alcohol consumption also have a very recognizable odor. Regardless of cause, the bad smell almost always originates in the mouth and not the stomach or elsewhere in the body. But one of the biggest challenges lies in actually determining how our breath smells in the first place, and it's unclear why. It may be that we're too acclimatized to the smell inside our own mouths to judge it, and methods like cupping your hands over your mouth or licking and smelling your wrist don't work perfectly either. One study showed that even when people do this, they tend to rate the smell subjectively, according to how bad they thought it was going to be. But there's one simple, if socially difficult, way of finding out how your breath smells. Just take a deep breath and ask a friend. It has no taste, color, or smell, and we often look right through it. It covers over 70% of the Earth, cycling from the oceans and rivers to the clouds and back again. It even makes up about 60% of our bodies. With all this water around and inside us, it's easy to take its presence for granted. But in the rest of the solar system, liquid water is almost impossible to find. So how did our planet end up with so much of this substance, and where did it come from? As you probably know, a water molecule consists of two basic parts. Hydrogen, the simplest of all elements, has been around since close to the beginning of our universe. Oxygen entered the scene several 100 million years later, after stars began to form. The massive pressure at the center of these fiery infernos was so great that hydrogen atoms fused together to form helium. Helium, in turn, fused to form heavier elements like beryllium, carbon, and oxygen in a process known as nucleosynthesis. When stars eventually collapsed and exploded into supernovas, these new elements were spread across the universe and combined into new compounds, like the now familiar H2O. These water molecules were present in the dusty cloud that formed our solar system, and more collided with our planet after its formation. But there's a big question that we don't have the answer to. How much water arrived on Earth? And when? If, as one theory goes, relatively small amounts of water were present on Earth when the rock formed, the high temperatures and lack of any surrounding atmosphere would have caused it to evaporate back into space. Water would have been unable to remain on the planet until hundreds of millions of years later, when our first atmosphere formed through a process called outgassing. This occurred when molten rock in the Earth's core released volcanic gases to the surface, creating a layer that could then trap escaping water. So how then did water get back to the planet? Scientists have long suspected that much of it was brought by ice-bearing comets, or more likely, asteroids that bombarded the Earth over millions of years. Recent research has challenged this theory. In examining carbonaceous chondrite meteorites that formed shortly after the birth of our solar system, scientists have found that not only did they contain water, but their mineral chemical composition matched rocks on Earth and samples from an asteroid that formed at the same time as our planet. This suggests that the Earth may have accumulated a substantial amount of water early on that was able to stay put despite the lack of an atmosphere, though asteroids may have brought more over the eons. If this turns out to be true, life may have formed much earlier than previously thought. So we do not yet definitively know whether the water on Earth came from its initial formation, later impacts, or some combination of the two. Regardless, the water that runs from our showers, drinking fountains, and faucets is something that didn't just come from a nearby lake or river, but first underwent a cosmic and chaotic journey to get here. Earthquakes have always been a terrifying phenomenon, and they've become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. Why do buildings collapse in an earthquake, and how can it be prevented? If you've watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently, or even splitting apart. But that's not really how it works. For one thing, most buildings are not located right on a fault line, and the shifting tectonic plates go much deeper than building foundations. So what's actually going on? In fact, the reality of earthquakes and their effect on buildings is a bit more complicated. To make sense of it, architects and engineers use models, like a two-dimensional array of lines representing columns and beams, or a single-line lollipop with circles representing the building's mass. Even when simplified to this degree, these models can be quite useful, as predicting a building's response to an earthquake is primarily a matter of physics. Most collapses that occur during earthquakes aren't actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to cause a certain amount of displacement. Along with the building's material type and the shape of its columns, stiffness is largely a matter of height. Shorter buildings tend to be stiffer and shift less, while taller buildings are more flexible. You might think that the solution is to build shorter buildings so that they shift as little as possible. But the 1985 Mexico City earthquake is a good example of why that's not the case. During the quake, many buildings between 6 and 15 stories tall collapsed. What's strange is that while shorter buildings nearby did keep standing, buildings taller than 15 stories were also less damaged. And the mid-sized buildings that collapsed were observed shaking far more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency. In an oscillating system, the frequency is how many back-and-forth movement cycles occur within a second. This is the inverse of the period, which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around. Increasing a building's mass slows down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So in the equation representing their relationship, stiffness and natural frequency are proportional to one another, while mass and natural frequency are inversely proportional. What happened in Mexico City was an effect called resonance, where the frequency of the earthquake's seismic waves happened to match the natural frequency of the mid-sized buildings. Like a well-timed push on a swing set, each additional seismic wave amplified the building's vibration in its current direction, causing it to swing even further back, and so on, eventually reaching a far greater extent than the initial displacement. Today, engineers work with geologists and seismologists to predict the frequency of earthquake motions at building sites in order to prevent resonance-induced collapses, taking into account factors such as soil type and fault type, as well as data from previous quakes. Low frequencies of motion will cause more damage to taller and more flexible buildings, while high frequencies of motion pose more threat to structures that are shorter and stiffer. Engineers have also devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibrations. In the end, it's not the sturdiest buildings that will remain standing, but the smartest ones.
You've probably heard of the Boston Tea Party, something about a bunch of angry colonists dressed as Native Americans throwing chests of tea into the water. But the story is far more complicated, full of imperial intrigue, corporate crisis, smuggling, and the grassroots origins of the American Revolution. The first thing you need to know about tea in the 1700s is that it was really popular. In England, each man, woman, and child consumed almost 300 cups of the stuff every year. And, since the English colonized America, Americans were crazy about tea too. By the 1760s, they were drinking over 1 million pounds of tea every year. So, when Britain wanted to increase taxes on tea in America, people were not happy, mostly because they had no say in tax decisions made in London. Remember that famous phrase, no taxation without representation? The American colonists had long believed that they were not subject to taxes imposed by legislature in which they lacked representation. In fact, rather than paying the taxes, they simply dodged the tax collectors. Since the east coast of America is hundreds of miles long, and British enforcement was lax, about 3/4 of the tea Americans were drinking was smuggled in, usually from Holland. But the British insisted that Parliament did have the authority to tax the colonists, especially after Britain went deeply into debt fighting the French in the 7 Years' War. To close the budget gap, London looked to Americans, and in 1767 imposed new taxes on a variety of imports, including the Americans' beloved tea. America's response? No thanks. They boycotted the importation of tea from Britain, and instead brewed their own. After a new bunch of British customs commissioners cried to London for troops to help with tax enforcement, things got so heated that the Redcoats fired on a mob in Boston, killing several people in what was soon called the Boston Massacre. Under the terms of the 1773 Tea Act, Parliament cooked up a new strategy. Now the East India Company would sell the surplus tea directly through hand-picked consignees in America. This would lower the price to consumers, making British tea competitive with the smuggled variety while retaining some of the taxes. But the colonists saw through the British ploy and cried, "Monopoly!" Now it's a cold and rainy December 16, 1773. About 5,000 Bostonians are crowded into the Old South Meeting House, waiting to hear whether new shipments of tea that have arrived down the harbor will be unloaded for sale. When the captain of one of the ships reported that he could not leave with his cargo on board, Sam Adams rose to shout, "This meeting can do no more to save the country." Cries of, "Boston harbor a teapot tonight," rang out from the crowd. And about 50 men, some apparently dressed as Native Americans, marched down to Griffin's Wharf, stormed aboard 3 ships, and threw 340 tea chests overboard. An infuriated British government responded with the so-called Coercive Acts of 1774, which, among other things, closed the port of Boston until the locals compensated the East India Company for the tea. That never happened. Representatives of the colonies gathered at Philadelphia to consider how best to respond to continued British repression. This First Continental Congress supported destruction of the tea, pledged to support a continued boycott, and went home in late October 1774, even more united in their determination to protect their rights and liberties. The Boston Tea Party began a chain reaction that led with little pause to the Declaration of Independence and a bloody rebellion, after which the new nation was free to drink its tea, more or less, in peace.
Hello everyone, let's begin our guided tour. Welcome to the Museum of Museums. Museums have been a part of human history for over 2,000 years, but they weren't always like the ones we visit today. The history of museums is far older and much stranger than you might imagine. We'll start over here in the Greek wing. Our word museum comes from the Greek museon, temples built for the muses, the goddesses of the arts and the sciences. Supplicants asked the muses to keep watch over academics and grant ingenuity to those they deemed worthy. The temples were filled with offerings of sculptures, mosaics, complex scientific apparatuses, poetic and literary inscriptions, and any other tribute that would demonstrate a mortal's worthiness for divine inspiration. We have arrived at the Mesopotamian wing. The first museum was created in 530 BC in what is now Iraq, and the first curator was actually a princess. Enigaldi Nana started to collect and house Mesopotamian antiquities in Egigpar, her house. When archaeologists excavated the area, they discovered dozens of artifacts neatly arranged in rows with clay labels written in 3 languages. She must have had interesting parties. The tradition of collecting and displaying intriguing items began to be mimicked, as you can see here in the Roman Empire wing. Treasure houses of politicians and generals were filled with the spoils of war, and royal menageries displayed exotic animals to the public on special occasions like gladiator tournaments. As you can see, we have a lion here and a gladiator, and, well, the janitor ought to be in this wing, clearly. Moving on, hurry along. The next step in the evolution of museums occurred in the Renaissance, when the study of the natural world was once again encouraged after almost a millennium of Western ignorance. Curiosity cabinets, also referred to as Wunderkammers, were collections of objects that acted as a kind of physical encyclopedia, showcasing artifacts. Just step into the wardrobe here, there you go, mind the coats, and we'll tour Ola Worm's cabinet. One of the most notable Wunderkammers belonged to a wealthy 17th century naturalist, antiquarian, and physician, Ola Worm. Ola Worm collected natural specimens, human skeletons, ancient runic texts, and artifacts from the New World. In other curiosity cabinets, you could find genetic anomalies, precious stones, works of art, and religious and historic relics. Oh my, you might not want to touch that. These cabinets were private, again, often in residencies, curated by their owners, rulers and aristocrats, as well as merchants and early scientists. Now, who hears a circus organ? In the 1840s, an enterprising young showman named Phineas T. Barnum purchased some of the more famous cabinets of curiosity from Europe and started Barnum's American Museum in New York City, a spectacular hodgepodge of zoo, lecture hall, wax museum, theater, and freak show that was known for its eclectic residents, such as bears, elephants, acrobats, giants, Siamese twins, a Fiji mermaid, and a bearded lady, along with a host of modern machinery and scientific instruments. Museums open to the public are a relatively new phenomenon. Before Barnum, the first public museums were only accessible by the upper and middle classes, and only on certain days. Visitors would have to apply to visit the museum in writing prior to admission, and only small groups could visit the museum each day. The Louvre famously allowed all members of the public into the museum, but only 3 days a week. In the 19th century, the museum as we know it began to take shape. Institutions like the Smithsonian were started so that objects could be seen and studied, not just locked away. American museums in particular commissioned experiments and hired explorers to seek out and retrieve natural samples. Museums became centers for scholarship and artistic and scientific discovery. This is often called the museum age. Nowadays, museums are open to everybody, are centers of learning and research, and are turning into more hands-on institutions. But the question of who gets to go is still relevant, as ticket prices can sometimes bar admission to those future scholars, artists, and targets of divine inspiration who can't afford to satisfy their curiosity. Thank you all for coming, and please feel free to stop by the gift shop of gift shops on your way out.
You might think you know a lot about Native Americans through popular movies, books, and classes in school, but it turns out that a lot of what we think we know about famous Native American figures isn't quite right. Take Sacagawea, for example. You probably remember her as a beautiful Indian woman who lived an exotic life, serving as the all-knowing guide for Lewis and Clark's famous expedition, right? Well, that's not exactly how it happened. Not much is known about Sacagawea's early childhood, but we do know that she was born in 1788 into the Agatica tribe of the Lemhi Shoshone in what is now Idaho. In 1800, when she was about 12 years old, Sacagawea and several other girls were kidnapped by a group of Hidatsu Indians. She was taken as a captive to a Hidatsu village in present-day North Dakota. Then she was sold to a French-Canadian fur trapper named Toussaint Charbonneau. Within a year or so, she was pregnant with their first child. Soon after she became pregnant, the Corps of Discovery arrived near the Hidatsu villages. Captains Meriwether Lewis and William Clark built Fort Mandan there and then started interviewing people to help guide them on their perilous expedition. They agreed to hire Sacagawea's husband, Charbonneau, with the understanding that his lovely wife would also come along as an interpreter. They figured her very presence would help any encounters with native tribes along the way. As Clark noted in his journal, "A woman with a party of men is a token of peace." Shortly thereafter, Sacagawea gave birth to a little boy named Jean-Baptiste Charbonneau. Clark called him Pompey. She carried Pompey on a board strapped to her back as the Corps of Discovery forged on. Besides interpreting the language when Lewis and Clark encountered Indians, Sacagawea's activities as a member of the Corps included digging for roots, collecting edible plants, and picking berries. In 1805, the boat they were riding in was capsized. She dove into the water, recovering all the important papers and supplies that would otherwise have been lost, including the journals and records of Lewis and Clark. Later that year, Captain Lewis and 3 men scouted 75 miles ahead of the expedition's main party, crossing the Continental Divide. The next day, they encountered a group of Shoshones. Not only did they prove to be Sacagawea's band, but their leader, Chief Kameawait, turned out to be her very own brother. After 5 years of separation since her kidnapping as a young girl, Sacagawea and Kameawait had an emotional reunion. Unfortunately, she quickly had to bid farewell to her beloved brother and continue on with the journey. At one point, the expedition became so difficult and freezing, the group was reduced to eating candles to survive. When temperatures finally became more bearable, Sacagawea found, dug, and cooked roots to help the group regain their strength. On the return trip, they encountered an Indian wearing a beautiful fur robe. Lewis and Clark wanted to bring the robe to Thomas Jefferson as a gift, but had nothing to trade for it. So, Sacagawea agreed to trade her most precious possession, her beaded belt, for the fur. A little over 2 years after the expedition began, it was finally over, ending in St. Louis. Today, we learn about Sacagawea in school as a heroic guide, but her life, like most everyone's, was much more complicated than history books sometimes give her credit for.
You and a fellow castaway are stranded on a desert island, playing dice for the last banana. You've agreed on these rules. You'll roll 2 dice, and if the biggest number is 1, 2, 3, or 4, player 1 wins. If the biggest number is 5 or 6, player 2 wins. Let's try twice more. Here, player 1 wins. And here, it's player 2. So who do you want to be? At first glance, it may seem like player 1 has the advantage, since she'll win if any one of 4 numbers is the highest. But actually, player 2 has an approximately 56% chance of winning each match. One way to see that is to list all the possible combinations you could get by rolling 2 dice, and then count up the ones that each player wins. These are the possibilities for the yellow die. These are the possibilities for the blue die. Each cell in the chart shows a possible combination when you roll both dice. If you roll a 4 and then a 5, we'll mark a player 2 victory in this cell. A 3 and a 1 gives player 1 a victory here. There are 36 possible combinations, each with exactly the same chance of happening. Mathematicians call these equiprobable events. Now we can see why the first glance was wrong. Even though player 1 has 4 winning numbers and player 2 only has 2, the chance of each number being the greatest is not the same. There is only a 1 in 36 chance that 1 will be the highest number, but there's an 11 in 36 chance that 6 will be the highest. So if any of these combinations are rolled, player 1 will win. And if any of these combinations are rolled, player 2 will win. Out of the 36 possible combinations, 16 give the victory to player 1, and 20 give player 2 the win. You could think about it this way, too. The only way player 1 can win is if both dice show a 1, 2, 3, or 4. A 5 or 6 would mean a win for player 2. The chance of one die showing 1, 2, 3, or 4 is 4 out of 6. The result of each die roll is independent from the other, and you can calculate the joint probability of independent events by multiplying their probabilities. So the chance of getting a 1, 2, 3, or 4 on both dice is 4 out of 6 times 4 out of 6, or 16 out of 36. Because someone has to win, the chance of player 2 winning is 36 out of 36 minus 16 out of 36, or 20 out of 36. Those are the exact same probabilities we got by making our table. But this doesn't mean that player 2 will win, or even that if you played 36 games as player 2, you'd win 20 of them. That's why events like dice rolling are called random. Even though you can calculate the theoretical probability of each outcome, you might not get the expected results if you examine just a few events. But if you repeat those random events many, many, many times, the frequency of a specific outcome, like a player 2 win, will approach its theoretical probability. That value we got by writing down all the possibilities and counting up the ones for each outcome. So, if you sat on that desert island playing dice forever, player 2 would eventually win 56% of the games, and player 1 would win 44%. But by then, of course, the banana would be long gone. Three and a half thousand years ago in Egypt, a noble pharaoh was the victim of a violent attack. But the attack was not physical. This royal had been dead for 20 years. The attack was historical, an act of damnatio memoriae, the damnation of memory. Somebody smashed the pharaoh's statues, took a chisel, and attempted to erase the pharaoh's name and image from history. Who was this pharaoh? And what was behind the attack? Here's the key. The pharaoh Hatshepsut was a woman. In the normal course of things, she should never have been pharaoh. Although it was legal for a woman to be a monarch, it disturbed some essential Egyptian beliefs. Firstly, the pharaoh was known as the living embodiment of the male god Horus. Secondly, disturbance to the tradition of rule by men was a serious challenge to Ma'at, a word for truth expressing a belief in order and justice, vital to the Egyptians. Hatshepsut had perhaps tried to adapt to this belief in the link between order and patriarchy through her titles. She took the name Ma'at Kare and sometimes referred to herself as Hatshepsu, with a masculine word ending. But apparently, these efforts didn't convince everyone. And perhaps someone erased Hatshepsut's image so that the world would forget the disturbance to Ma'at and Egypt could be balanced again. Hatshepsut, moreover, was not the legitimate heir to the throne, but a regent, a kind of stand-in co-monarch. The Egyptian kingship traditionally passed from father to son. It passed from Thutmose I to his son Thutmose II, Hatshepsut's husband. It should have passed from Thutmose II directly to his son Thutmose III, but Thutmose III was a little boy when his father died. Hatshepsut, the dead pharaoh's chief wife and widow, stepped in to help as her stepson's regent, but ended up ruling beside him as a fully fledged pharaoh. Perhaps Thutmose III was angry about this. Perhaps he was the one who erased her images. It's also possible that someone wanted to dishonor Hatshepsut because she was a bad pharaoh. But the evidence suggests she was actually pretty good. She competently fulfilled the traditional roles of the office. She was a great builder. Her mortuary temple, Djeser Djeseru, was an architectural phenomenon at the time and is still admired today. She enhanced the economy of Egypt, conducting a very successful trade mission to the distant land of Punt. She had strong religious connections. She even claimed to be the daughter of the state god Amun. And she had a successful military career, with a Nubian campaign and claims she fought alongside her soldiers in battle. Of course, we have to be careful when we assess the success of Hatshepsut's career, since most of the evidence was written by Hatshepsut herself. She tells her own story in pictures and writing on the walls of her mortuary temple and the red chapel she built for Amun. So who committed the crimes against Hatshepsut's memory? The most popular suspect is her stepson, nephew, and co-ruler, Thutmose III. Did he do it out of anger because she stole his throne? This is unlikely, since the damage wasn't done until 20 years after Hatshepsut died. That's a long time to hang on to anger and then act in a rage. Maybe Thutmose III did it to make his own reign look stronger, but it is most likely that he or someone else erased the images so that people would forget that a woman ever sat on Egypt's throne. This gender anomaly was simply too much of a threat to Ma'at and had to be obliterated from history. Happily, the ancient censors were not quite thorough enough. Enough evidence survived for us to piece together what happened, so the story of this unique, powerful woman can now be told. The area surrounding the North Pole may seem like a frozen and desolate environment where nothing ever changes, but it is actually a complex and finely balanced natural system, and its extreme location makes it vulnerable to feedback processes that can magnify even tiny changes in the atmosphere. In fact, scientists often describe the Arctic as the canary in the coal mine when it comes to predicting the impact of climate change. One major type of climate feedback involves reflectivity. White surfaces like snow and ice are very effective at reflecting the sun's energy back into space, while darker land and water surfaces absorb much more incoming sunlight. When the Arctic warms just a little, some of the snow and ice melts, exposing the ground and ocean underneath. The increased heat absorbed by these surfaces causes even more melting, and so on. And although the current situation in the Arctic follows the warming pattern, the opposite is also possible. A small drop in temperatures would cause more freezing, increasing the amount of reflective snow and ice. This would result in less sunlight being absorbed and lead to a cycle of cooling, as in previous ice ages. Arctic sea ice is also responsible for another feedback mechanism through insulation. By forming a layer on the ocean surface, the ice acts as a buffer between the frigid Arctic air and the relatively warmer water underneath. But when it thins, breaks, or melts in any spot, heat escapes from the ocean, warming the atmosphere and causing more ice to melt in turn. Both of these are examples of positive feedback loops, not because they do something good, but because the initial change is amplified in the same direction. A negative feedback loop, on the other hand, is when the initial change leads to effects that work in the opposite direction. Melting ice also causes a type of negative feedback by releasing moisture into the atmosphere. This increases the amount and thickness of clouds present, which can cool the atmosphere by blocking more sunlight. But this negative feedback loop is short-lived due to the brief Arctic summers. For the rest of the year, when sunlight is scarce, the increased moisture and clouds actually warm the surface by trapping the Earth's heat, turning the feedback loop positive for all but a couple of months. While negative feedback loops encourage stability by pushing a system towards equilibrium, positive feedback loops destabilize it by enabling larger and larger deviations. And the recently increased impact of positive feedbacks may have consequences far beyond the Arctic. On a warming planet, these feedbacks ensure that the North Pole warms at a faster rate than the equator. The reduced temperature differences between the two regions may lead to slower jet stream winds and less linear atmospheric circulation in the middle latitudes, where most of the world's population lives. Many scientists are concerned that shifts in weather patterns will last longer and be more extreme, with short-term fluctuations becoming persistent cold snaps, heat waves, droughts, and floods. So the Arctic's sensitivity doesn't just serve as an early warning alarm for climate change for the rest of the planet. Its feedback loops can affect us in much more direct and immediate ways. As climate scientists often warn, what happens in the Arctic doesn't always stay in the Arctic.
In 2008, something incredible happened. A man was cured of HIV. In over 70 million HIV cases, that was a first, and so far a last. We don't yet understand exactly how he was cured. We can cure people of various diseases, such as malaria and hepatitis C, so why can't we cure HIV? Well, first, let's examine how HIV infects people and progresses into AIDS. HIV spreads through exchanges of bodily fluids. Unprotected sex and contaminated needles are the leading cause of transmission. It fortunately cannot spread through air, water, or casual contact. Individuals of any age, sexual orientation, gender, and race can contract HIV. Once inside the body, HIV infects cells that are part of the immune system. It particularly targets helper T cells, which help defend the body against bacterial and fungal infections. HIV is a retrovirus, which means it can write its genetic code into the genome of infected cells, co-opting them into making more copies of itself. During the first stage of HIV infection, the virus replicates within helper T cells, destroying many of them in the process. During this stage, patients often experience flu-like symptoms, but are typically not yet in mortal danger. However, for a period ranging from a few months to several years, during which time the patient may look and feel completely healthy, the virus continues to replicate and destroy T cells. When T cell counts drop too low, patients are in serious danger of contracting deadly infections that healthy immune systems can normally handle. This stage of HIV infection is known as AIDS. The good news is, there are drugs that are highly effective at managing levels of HIV and preventing T cell counts from getting low enough for the disease to progress to AIDS. With antiretroviral therapy, most HIV-positive people can expect to live long and healthy lives and are much less likely to infect others. However, there are two major catches. One is that HIV-positive patients must keep taking their drugs for the rest of their lives. Without them, the virus can make a deadly comeback. So, how do these drugs work? The most commonly prescribed ones prevent the viral genome from being copied and incorporated into a host cell's DNA. Other drugs prevent the virus from maturing or assembling, causing HIV to be unable to infect new cells in the body. But HIV hides out somewhere our current drugs cannot reach it, inside the DNA of healthy T cells. Most T cells die shortly after being infected with HIV. But in a tiny percentage, the instructions for building more HIV viruses lies dormant, sometimes for years. So even if we could wipe out every HIV virus from an infected person's body, one of those T cells could activate and start spreading the virus again. The other major catch is that not everyone in the world has access to the therapies that could save their lives. In sub-Saharan Africa, which accounts for over 70% of HIV patients worldwide, antiretrovirals reached only about 1 in 3 HIV-positive patients in 2012. There is no easy answer to this problem. A mix of political, economic, and cultural barriers makes effective prevention and treatment difficult. And even in the US, HIV still claims more than 10,000 lives per year. However, there is ample cause for hope. Researchers may be closer than ever to developing a true cure. One research approach involves using a drug to activate all cells harboring the HIV genetic information. This would both destroy those cells and flush the virus out into the open, where our current drugs are effective. Another is looking to use genetic tools to cut the HIV DNA out of cells' genomes altogether. And while one cure out of 70 million cases may seem like terrible odds, one is immeasurably better than 0. We now know that a cure is possible, and that may give us what we need to beat HIV for good.
You probably don't need to be told how important your brain is. After all, every single thing you experience, your thoughts and your actions, your perceptions and your memories, are processed here in your body's control center. But if this already seems like a lot for a single organ to handle, it's actually only a small part of what the brain does. Most of its activities are ones you'd never be aware of, unless they suddenly stopped. The brain is made up of billions of neurons and trillions of connections. Neurons can be activated by specific stimuli or thoughts, but they are also often spontaneously active. Some fire cyclically in a set pattern. Others fire rapidly in short bursts before switching off, or remain quiet for long periods until thousands of inputs from other neurons line up in just the right way. On a large scale, this results in elaborate rhythms of internally generated brain activity humming quietly in the background whether we're awake, asleep, or trying not to think about anything at all. And these spontaneously occurring brain functions form the foundation upon which all other brain functions rely. The most crucial of these automatically occurring activities are the ones that keep us alive. For example, while you've been paying attention to this video, spontaneous activity in your brain has been maintaining your breathing at 12 to 16 breaths a minute, making sure that you don't suffocate. Without any conscious effort, signals from parts of your brainstem are sent through the spinal cord to the muscles that inflate your lungs, making them expand and contract, whether or not you're paying attention. The neuronal circuits underlying such rhythmic spontaneous activity are called central pattern generators and control many simple repetitive behaviors like breathing, walking, and swallowing. Ongoing neural activity also underlies our sensory perception. It may seem that the neurons in your retina that translate light into neural signals would remain quiet in the dark, but in fact, the retinal ganglion cells that communicate with the brain are always active, and the signals they send are increases and decreases in the rate of activity, rather than separate bursts. So at every level, our nervous system is teeming with spontaneous activity that helps it interpret and respond to any signals it might receive. And our brain's autopilot isn't just limited to our basic biological functions. Have you ever been on the way home, started thinking about what's for dinner, and then realized you don't remember walking for the past 5 minutes? While we don't understand all the details, we do know that the ongoing activity in multiple parts of your brain is somehow able to coordinate what is actually a complex task involving both cognitive and motor functions, guiding you down the right path and moving your legs while you're getting dinner figured out. But perhaps the most interesting thing about spontaneous brain function is its involvement in one of the most mysterious and poorly understood phenomena of our bodies: sleep. You may shut down and become inactive at night, but your brain doesn't. While you sleep, ongoing spontaneous activity gradually becomes more and more synchronized, eventually developing into large, rhythmic neural oscillations that envelop your brain. This transition to the more organized rhythms of sleep starts with small clusters of neurons tucked in the hypothalamus. Despite their small number, these neurons have a huge effect in turning off brainstem regions that normally keep you awake and alert, letting other parts like the cortex and thalamus slowly slip into their own default rhythms. The deeper we fall into sleep, the slower and more synchronized this rhythm becomes, with the deepest stages dominated by large amplitude, low frequency delta waves. But surprisingly, in the middle of this slow wave sleep, the brain's synchronized spontaneous activity repeatedly transitions into the sort of varied bursts that occur when we're wide awake. This is the sleep stage known as REM sleep, where our eyes move rapidly back and forth as we dream. Neuroscientists are still trying to answer many fundamental questions about sleep, such as its role in rejuvenating cognitive capacity, cellular homeostasis, and strengthening memory. And more broadly, they are exploring how it is that the brain can accomplish such important and complex tasks, such as driving or even breathing, without our awareness. But for now, until we are better able to understand the inner workings of their spontaneous functioning, we need to give our brains credit for being much smarter than we ourselves are. For most of us, 2 degrees Celsius is a tiny difference in temperature, not even enough to make you crack a window. But scientists have warned that as CO2 levels in the atmosphere rise, an increase in the Earth's temperature by even this amount can lead to catastrophic effects all over the world. How can such a small, measurable change in one factor lead to massive and unpredictable changes in other factors? The answer lies in the concept of a mathematical tipping point, which we can understand through the familiar game of billiards. The basic rule of billiard motion is that a ball will go straight until it hits a wall, then bounce off at an angle equal to its incoming angle. For simplicity's sake, we'll assume that there is no friction, so balls can keep moving indefinitely. And to simplify the situation further, let's look at what happens with only one ball on a perfectly circular table. As the ball is struck and begins to move according to the rules, it follows a neat star-shaped pattern. If we start the ball at different locations or strike it at different angles, some details of the pattern change, but its overall form remains the same. With a few test runs and some basic mathematical modeling, we can even predict a ball's path before it starts moving, simply based on its starting conditions. But what would happen if we made a minor change in the table's shape by pulling it apart a bit and inserting 2 small straight edges along the top and bottom? We can see that as the ball bounces off the flat sides, it begins to move all over the table. The ball is still obeying the same rules of billiard motion, but the resulting movement no longer follows any recognizable pattern. With only a small change to the constraints under which the system operates, we have shifted the billiard motion from behaving in a stable and predictable fashion to fluctuating wildly, thus creating what mathematicians call chaotic motion. Inserting the straight edges into the table acts as a tipping point, switching the system's behavior from one type of behavior, regular, to another type of behavior, chaotic. So what implications does this simple example have for the much more complicated reality of the Earth's climate? We can think of the shape of the table as being analogous to the CO2 level and Earth's average temperature, constraints that impact the system's performance in the form of the ball's motion or the climate's behavior. During the past 10,000 years, the fairly constant CO2 atmospheric concentration of 270 parts per million kept the climate within a self-stabilizing pattern, fairly regular and hospitable to human life. But with CO2 levels now at 400 parts per million, and predicted to rise to between 500 and 800 parts per million over the coming century, we may reach a tipping point where even a small additional change in the global average temperature would have the same effect as changing the shape of the table, leading to a dangerous shift in the climate's behavior, with more extreme and intense weather events, less predictability, and most importantly, less hospitability to human life. The hypothetical models that mathematicians study in detail may not always look like actual situations, but they can provide a framework and a way of thinking that can be applied to help understand the more complex problems of the real world. In this case, understanding how slight changes in the constraints impacting a system can have massive impacts gives us a greater appreciation for predicting the dangers that we cannot immediately perceive with our own senses. Because once the results do become visible, it may already be too late. Humans have been fascinated with speed for ages. The history of human progress is one of ever-increasing velocity, and one of the most important achievements in this historical race was the breaking of the sound barrier. Not long after the first successful airplane flights, pilots were eager to push their planes to go faster and faster. But as they did so, increased turbulence and large forces on the plane prevented them from accelerating further. Some tried to circumvent the problem through risky dives, often with tragic results. Finally, in 1947, design improvements such as a movable horizontal stabilizer, the all-moving tail, allowed an American military pilot named Chuck Yeager to fly the Bell X-1 aircraft at 1,127 kilometers per hour, becoming the first person to break the sound barrier and travel faster than the speed of sound. The Bell X-1 was the first of many supersonic aircraft to follow, with later designs reaching speeds over Mach 3. Aircraft traveling at supersonic speed create a shockwave with a thunder-like noise known as a sonic boom, which can cause distress to people and animals below, or even damage buildings. For this reason, scientists around the world have been looking at sonic booms, trying to predict their path in the atmosphere, where they will land, and how loud they will be. To better understand how scientists study sonic booms, let's start with some basics of sound. Imagine throwing a small stone in a still pond. What do you see? The stone causes waves to travel in the water at the same speed in every direction. These circles that keep growing in radius are called wave fronts. Similarly, even though we cannot see it, a stationary sound source, like a home stereo, creates sound waves traveling outward. The speed of the waves depends on factors like the altitude and temperature of the air they move through. At sea level, sound travels at about 1,225 kilometers per hour. But instead of circles on a two-dimensional surface, the wave fronts are now concentric spheres, with the sound traveling along rays perpendicular to these waves. Now imagine a moving sound source, such as a train whistle. As the source keeps moving in a certain direction, the successive waves in front of it will become bunched closer together. This greater wave frequency is the cause of the famous Doppler effect, where approaching objects sound higher pitched. But as long as the source is moving slower than the sound waves themselves, they will remain nested within each other. It's when an object goes supersonic, moving faster than the sound it makes, that the picture changes dramatically. As it overtakes sound waves it has emitted while generating new ones from its current position, the waves are forced together, forming a Mach cone. No sound is heard as it approaches an observer because the object is traveling faster than the sound it produces. Only after the object has passed will the observer hear the sonic boom. Where the Mach cone meets the ground, it forms a hyperbola, leaving a trail known as the boom carpet as it travels forward. This makes it possible to determine the area affected by a sonic boom. What about figuring out how strong a sonic boom will be? This involves solving the famous Navier-Stokes equations to find the variation of pressure in the air due to the supersonic aircraft flying through it. This results in the pressure signature known as the N wave. What does this shape mean? Well, the sonic boom occurs when there is a sudden change in pressure, and the N wave involves two booms, one for the initial pressure rise at the aircraft's nose, and another for when the tail passes and the pressure suddenly returns to normal. This causes a double boom, but it is usually heard as a single boom by human ears. In practice, computer models using these principles can often predict the location and intensity of sonic booms for given atmospheric conditions and flight trajectories, and there is ongoing research to mitigate their effects. In the meantime, supersonic flight over land remains prohibited. So are sonic booms a recent creation? Not exactly. While we try to find ways to silence them, a few other animals have been using sonic booms to their advantage. The gigantic Diplodocus may have been capable of cracking its tail faster than sound, at over 1,200 kilometers per hour, possibly to deter predators. Some types of shrimp can also create a similar shock wave underwater, stunning or even killing prey at a distance with just a snap of their oversized claw. So while we humans have made great progress in our relentless pursuit of speed, it turns out that nature was there first.
Flying through the night, I watch over this world, a silent guardian, a watchful protector, a dark knight.
Okay, fine, so I'm not Batman. I'm just a bat. But like Batman, I'm often misunderstood. People think I'm scary, strange, and dangerous. If they only knew my story, though, I'd be cheered as a hero. When people think of bats, many think of vampires who want to suck their blood. But the truth is that out of over 1,200 bat species, only 3 are vampire bats. Out of these 3, only 1 prefers the blood of mammals. And even these bats mostly feed on cattle. Maybe that still doesn't seem so great, but vampire bats can be a great help to humans. A chemical known as desmoteplase found in vampire bat saliva helps break down blood clots and is being tested by recovering stroke victims. Of the remaining 1,000+ species of bats, about 70% feed on insects. These bats help control the real vampires, mosquitoes, whose nasty bites are not just annoying, but spread diseases like West Nile virus. A single little brown bat can eat 1,000 insects every hour, and a colony of Mexican free-tailed bats can eat several tons of moths in just one night. In the United States alone, bats provide an estimated $3.7 billion worth of free pest control for farmers, which benefits everyone who eats the foods that they grow. Fruit bats, also called megabats because of their large size, are important for the role they play in plant pollination. By traveling between flowers while feeding on nectar and fruits, these bats transport the pollen and seeds that help plants reproduce. In Southeast Asia, for example, the cave nectar bat is the only pollinator of the durian fruit. Other bats pollinate peaches, bananas, and the agave plants that tequila is made from. Without them, many of our food plants would be unable to produce the tasty fruits we enjoy. As heroes of the ecosystem, bats have their own unique utility belts. Bats have been a source of inspiration for the design of flying robots and even an energy-efficient spy plane, as they are the only mammal capable of true powered flight. Echolocation, a type of biological sonar, is also used by bats as a way to navigate and find prey in the dark. Although there's a common misconception that bats are blind, in truth, all species of bats have sight, and some have even adapted large eyes to see better in dim lighting. Many people worry about getting infected by bats, and like any other animals, Bats can carry diseases like rabies. In reality, though, less than half of 1% of all bats carry this virus. That's about the same odds as getting the same result on a coin flip 8 times in a row. The perception that bats are often diseased may come from the fact that sick bats, who may show unusual behavior, emerge during the daytime, or be unable to fly, are more likely to be encountered by people. So a good way to protect yourself is to protect bats as well, keeping them healthy, protecting their habitats, and reducing their risk of transmitting disease. In North America, bats are threatened by a devastating sickness called white nose syndrome. This fungal infection causes bats to wake up while hibernating during the winter. Unable to find food, they expend large amounts of energy and eventually starve to death. White nose syndrome has wiped out entire caves full of bats, with a mortality rate that can exceed 90%. Climate change and habitat destruction also pose serious threats to bat populations. For example, in January 2014, a record heat wave in Australia caused over 100,000 bats to die from heat exhaustion. Some people just want to watch the world burn, and bats all over the world are threatened by damage to the places that we call home, including mangrove swamps, old-growth forests, and of course, bat caves. So even though I'm the hero of the story, I do need to be saved. And now that you know the true story about us bats, you can learn how to protect such heroic animals. Install a properly designed bat box, one of the easiest ways to provide shelter for bats. Discourage the use of pesticides, which can harm bats when we try to feed on the insects you want to get rid of in the first place. Avoid going into caves where you might disturb hibernating bats, and always decontaminate your gear after visiting a cave. If you have unwanted bats living in an attic or barn, contact your local government to safely and humanely relocate us. And if you come across a bat, do not attempt to handle it, but instead call animal control. Batman might want to keep his identity secret, but a great way to help real bats is by continuing to learn about them and spreading the truth that they are real heroes, even if their good deeds are often unseen. You have about 20,000 genes in your DNA. They encode the molecules that make up your body, from the keratin in your toenails, to the collagen at the tip of your nose, to the dopamine surging around inside your brain. Other species have genes of their own. A spider has genes for spider silk. An oak tree has genes for chlorophyll, which turns sunlight into wood. So where did all those genes come from? It depends on the gene. Scientists suspect that life started on Earth about 4 billion years ago. The early life forms were primitive microbes, with a basic set of genes for the basic tasks required to stay alive. They passed down those basic genes to their offspring through billions of generations. Some of them still do the same jobs in our cells today, like copying DNA. But none of those microbes had genes for spider silk or dopamine. There are a lot more genes on Earth today than there were back then. It turns out that a lot of those extra genes were born from mistakes. Each time a cell divides, it makes new copies of its DNA. Sometimes it accidentally copies the same stretch of DNA twice. In the process, it may make an extra copy of one of its genes. At first, the extra gene works the same as the original one, but over the generations, it may pick up new mutations. Those mutations may change how the new gene works, and that new gene may duplicate again. A surprising number of our mutated genes emerged more recently, many in just the past few million years. The youngest evolved after our own species broke off from our cousins, the apes. While it may take over 1 million years for a single gene to give rise to a whole family of genes, scientists are finding that once the new genes evolve, they can quickly take on essential functions. For example, we have hundreds of genes for the proteins in our noses that grab odor molecules. The mutations let them grab different molecules, giving us the power to perceive trillions of different smells. Sometimes mutations have a bigger effect on new copies of genes. They may cause a gene to make its protein in a different organ, or at a different time of life. Or the protein may start doing a different job altogether. In snakes, for example, there's a gene that makes a protein for killing bacteria. Long ago, the gene duplicated, and the new copy mutated. That mutation changed the signal in the gene about where it should make its protein. Instead of becoming active in the snake's pancreas, it started making this bacteria-killing protein in the snake's mouth. So when the snake bit its prey, this enzyme got into the animal's wound. And when this protein proved to have a harmful effect and helped the snake catch more prey, it became favored. So now what was a gene in the pancreas makes a venom in the mouth that kills the snake's prey. And there are even more incredible ways to make a new gene. The DNA of animals and plants and other species contain huge stretches without any protein-coding genes. As far as scientists can tell, it's mostly random sequences of genetic gibberish that serve no function. These stretches of DNA sometimes mutate, just like genes do. Sometimes those mutations turn the DNA into a place where a cell can start reading it. Suddenly, the cell is making a new protein. At first, the protein may be useless or even harmful, but more mutations can change the shape of the protein. The protein may start doing something useful, something that makes an organism healthier, stronger, better able to reproduce. Scientists have found these new genes at work in many parts of animal bodies. So our 20,000 genes have many origins, from the origin of life to new genes still coming into existence from scratch. As long as life is here on Earth, it will be making new genes.